In a comparative static analysis of constraint optimization, maximization or minimization, problem is often helpful to use an approach based on envelope theorem rather than implicit function theorem. In case of implicit function theorem, what we are doing, we are considering an objective function, we are considering a constraint, we are framing a Lagrangian expression, considering set of first order conditions, solving first order conditions, we are deriving the values of x1 star, x2 star, plugging those values, in the solving x1 star, x2 star in terms of the parameters of the model, plugging these values to the original objective function, and then deriving the optimum value, the maximum value or the minimum value, considering the second order condition to ensure whether it is maximum or minimum. Okay, so simultaneously solving several equations to find out these values. Okay, instead of doing this thing, what we can do, we can consider the Lagrangian expression and the value function, take the derivatives with respect to alpha, okay, or with respect to parameters of the model, and we may show, if I take the comparative static with respect to V, that will be very, very similar to if I consider the comparative statics with respect to L. So in the comparative static analysis of constraint maximization or minimization problem, it is often helpful to use the approach based on the envelope theorem rather than implicit function theorem. So suppose we have the problem max, the objective function f of x1, x2 alpha, subject to the constraint g of x1, x2, where the parameter is alpha, is equal to 0. So please write down this expression. To begin with, suppose we have the objective function max x1, x2, semicolon alpha, where alpha is the parameter. Actually, we have to maximize x1, x2 only, in terms of alpha, and we have a constraint g of x1, x2 alpha, where alpha is an exogenous variable. It is fixed, it is constant. The required Lagrangian expression is L is equal to x1, x2, comma lambda. When we are writing the Lagrangian expression, a new thing is coming, that is Lagrange multiplier. So L is becoming a function of x1, x2 lambda. The alpha will be there, that is the exogenous variable, or you can treat it as a constant, as a parameter. L is a combination of the objective function as well as the constraint. So L is basically f of x1, x2 alpha plus lambda g of x1, x2 alpha. Then we consider a set of first order conditions. If I have two variables, we will have two first order conditions and another condition in terms of Lagrange multiplier. If I have three variables, we will have three first order conditions. We will take derivative of L with respect to x1, x2, x3, and then we will have the constraint. That is, we will consider dL by d lambda. So these are the first order conditions we get. If we assume function f and g possesses a continuous first and second order derivatives, we can also present these particular determinant, which has a particular name, bordered Hessian determinant. So we can frame this bordered Hessian determinant, which is not equal to 0. And then we can apply the implicit function theorem to solve the value of x1, x2 in terms of alpha. In other words, this is equivalent to say,
for the previous slide once.
What is the problem?
No, ma'am, I was just checking this thing. Thank you. I wrote it. Thank you.
This is equivalent to say we can solve for endogenous variables as differentiable functions of the exogenous variables in the neighborhood of the optimal point, so that the value of the function f in the same neighborhood is f of x1 as a function of alpha, x2 as a function of alpha, then alpha is the exogenous variable, is equivalent to v alpha. So what we did, just we are writing that, we get a set of first order conditions, we solve those first order conditions, derive the values of x1 and x2 in terms of alpha. Okay, and write it as a value function, v of alpha. When we write the entire function in terms of the parameter of the model, we call it the value function. V is known as the value function. It depends on exogenous variable in the problem or parameter in the problem, alpha. Okay. So now we are starting our background to discuss the envelope theorem. We are starting our background to discuss the envelope theorem. This part, up to this part, we discuss the matter of implicit value function approach. Okay. Now we are starting the background which we will utilize to state the envelope theorem. So what we are doing, we are writing L in terms of the parameters of the model. We are writing L in terms of the parameters of the model. Okay. So now it will be better if you do the things with me. So L I am writing as function of parameters of the model. L is equal to f of x1, x2 alpha. So all x1 and x2 are functions of alpha. Then there is lambda into the constraint. Okay. So lambda, which is also a function of alpha, into g as a function of x1, x2 alpha. So both x1 and x2 are functions of alpha. So we are writing the expression as f of x1, x2 alpha plus lambda g of x1, x2 alpha. So this is our Lagrangian expression in terms of the parameter of the model. So take derivative of this L with respect to alpha. Slowly take the derivative of this L with respect to alpha. And please check whether you are getting the values which I got. So first I am taking the derivative for the first expression. If I'm getting f1 dx1 by d alpha plus f2, that is del f by del x2 into dx2 by d alpha. I'm totally differentiating it. Plus del f by del alpha then there is product lambda into g. So I'm keeping g fixed, taking the derivative of lambda with respect to alpha. So g into d lambda by d alpha. Then I'm taking or keeping lambda fixed and taking the derivative of g with respect to x1, x2 and alpha. So I'm getting lambda into g1, that is del g by del x1 into dx1 by d alpha, plus lambda del g by del x2 into dx2 by d alpha, plus lambda into del g by del alpha, that is g alpha. So we are getting all these 7 terms. So please check whether you are also getting these terms. So once you get these terms, take common, dx1 by d alpha common, dx2 by d alpha common. So take dx1 by d alpha and dx2 by d alpha common. and check whether you are getting the third line or not. So please let me know once you get the third line, once you get this one. If there is any mistake or there is any problem regarding understanding the matter, please let me know. Is it okay?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
I hope everybody is getting this. First, these 7 terms. And from there, if I take dx1 by d alpha, dx2 by d alpha common, we are getting this format. Now, at optimum, following the first order conditions, we get f1 plus lambda g1 is equal to 0. So if you consider the optimization technique, be it with respect to the utility maximization, be it with respect to cost minimization, output maximization, whatever, we got this format. f1 plus lambda g1 is equal to 0, f2 plus lambda g2 is equal to 0, and the constraint itself we got when we took the derivative with respect to alpha, or with respect to lambda, the Lagrange multiplier. So are you familiar? Can you remember all these 3 equations? This set of equations? Is it okay?
Yes, ma'am.
Yes, ma'am.
Okay, so what we will do, we will put this set of equations in this last equation derived. So f1 plus lambda g1 is equal to 0. So this first entire term will be equal to 0. Then f2 plus lambda g2 is equal to 0. So the second entire term will vanish. G is equal to 0. So the third term will also vanish. So dl by d alpha is equal to f alpha plus lambda g alpha. Okay. So finally what we are getting, dl by d alpha is nothing but f alpha plus lambda g alpha, which is equivalent to del L by del alpha, which is equivalent to del L by del alpha as well, because del F by del alpha plus lambda del G by del alpha, that we are getting. So is this equation okay to all of you? Are you understanding? dl by d alpha is equal to f alpha plus lambda g alpha.
Yes, ma'am.
Very good. So could you complete up to this?
Yes, ma'am.
Yes,
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 ma'am.
ma'am.
Okay.
Yes, ma'am.
Next, we will consider the value function. V as a function of x1, which is function of alpha, x2, which is also a function of alpha, and alpha. So we will consider the value function, and we will find out dv by d alpha. We will find out dv by d alpha. Okay, so okay, before going to that, so in the slide, let's check what we have in the slide. So it is dl by d alpha. Already we did this. Dl by d alpha is equivalent to del L by del alpha. That is, although a change in alpha induces changes in the values of the endogenous variables. That is, dx1 by d alpha, dx2 by d alpha, all these things are non-zero. These are not equal to 0. So although a change in alpha induces changes in the values of the endogenous variables, for small enough changes at the optimum point, the effect of these changes on Lagrangian function can be ignored because the partial derivatives of Lagrange function with respect to endogenous variables are 0 at that point. Okay, so what we could do, we at optimum, we could set this equal to 0, this equal to 0, okay, and g is equal to 0. So we could, though dx1 by d alpha is not 0, dx2 by d alpha not 0, at optimum we got this f1 plus lambda g1 and f2 plus lambda g2. These things are equal to 0. Okay, so for small enough changes at the optimum point, the effect of these changes on Lagrangian function can be ignored because the partial derivatives of the Lagrange function with respect to the endogenous variables are 0 at that point. Okay. The envelope theorem establishes a connection between the derivatives of the value function and the derivatives of the Lagrange function with respect to the parameter alpha at optimal point. Okay, that is, we can show that dv by d alpha is absolutely equal to dl by d alpha at optimum. Dv by d alpha is absolutely equal to dl by d alpha. Why? Because at optimum, all these parts are equal to 0, and for that matter we can ignore the change in x1 at alpha, change in x2 with respect to alpha in the neighborhood of optimum. Okay, so next we will actually find out dv by d alpha and show the equality between dl by d alpha and dv by d alpha. So we are going for that part. So first, write down the value function. The value function is given by v is equal to f of x1 as a function of alpha, x2 as a function of alpha, and the exogenous variable or parameter, whatever you say, alpha. Then you consider dv by d alpha. Total derivative. So that will be del f by del x1 into dx1 by d alpha. Plus del f by del x2 into dx2 by d alpha plus del f by del alpha. Now, following the first order conditions in context of any optimization technique, when we do the implicit functional format, we get these two first order conditions when we take the derivative with respect to alpha. These two equations we get. Actually, we get f1 plus lambda g1 is equal to 0, f2 plus lambda G2 is equal to 0. So from there we can write basically F1 is equal to minus lambda G1 and F2 is equal to minus lambda G2. Okay, so what I am doing in place of F1 and F2, I am plugging these minus lambda G1 and minus lambda G2. So I can keep minus lambda common and rewrite dV by d alpha in this format. So please check whether you are also getting the same thing. If anyone have any problem, please ask me. Could you complete up to this? Dv by d alpha is equal to minus lambda into g1 dx1 by d alpha plus g2 dx2 by d alpha plus f alpha. Up to this, it's complete. Understandable?
Yes.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Now I'm simply considering the constraint. Actually, this approach you considered for all the comparative static analysis. You took the value function, took derivative of this with respect to sometimes W1, W2, Y, sometimes with respect to W1, W2, P, depending on the nature of the function. You took the derivatives in this format and then you took the constraint and took derivative of the constraint with respect to similar set of parameters. So here also I am doing that. Now from the constraint, gx1 plus x2 alpha is equal to 0. From this constraint, this equal to 0, I am taking the total derivative. So I am getting g1 dx1 by d alpha plus g2, that is del g by del x2 into dx2 by d alpha is plus g alpha, that is del g by del alpha is equal to 0. I can keep minus g alpha to the right hand side and write the equation as this: g1 dx1 by d alpha plus g2 dx2 by d alpha is equal to minus g alpha. Once I get this thing, I am plugging this minus g alpha in this place. I am plugging minus g alpha here. So I am getting dv by d alpha is equal to lambda g alpha plus f alpha. This equation. So everybody is getting this?
Yes, ma'am.
So is it similar to dl by d alpha we got?
Yes, ma'am. Yes, ma'am. They're
dl by
equal.
d alpha was f alpha plus lambda g alpha, the same thing?
Yes, ma'am.
Yes, ma'am.
So there is an equivalence between these two. dl by d alpha, that is, we can consider the Lagrangian expression at optimum. That is, we are considering the original objective with respect to constraint at optimum. Okay, and that is equivalent to dv by d alpha. That is, if I consider the value function and we take the derivative with respect to alpha, we are getting the same solution. dl by d alpha is equivalent to dv by d alpha. So we can consider the objective function and the constraint in a single equation, that is in the Lagrangian expression, can take the derivative with respect to parameter. This will give us same solution to if I consider the value function and take the derivative with respect to the parameter. This is known as envelope theorem. So we can start with the basic objective function, take the derivative with respect to alpha to discuss the comparative static results, or we can consider the value function and take the derivatives with respect to the parameters. We will get the identical result. We will get the same result. This is known as envelope theorem. Okay, so these steps are there. Okay, so finally, dv by d alpha is equal to del L by del alpha. This is the form of envelope theorem. This is the form of envelope theorem. Okay, so this is the idea. Any question, any problem with respect to any step or understanding any part? Before that, the envelope theorem tells us that we can find the effect of a change in the exogenous variable on the optimized value of the objective function simply by taking partial derivative of the Lagrangian function with respect to the exogenous variable at the optimal solution to the problem. I'm repeating, it tells that we can find the effect of change in the exogenous variable on the optimized value, that is the v, the value function of the objective function, simply by taking the partial derivatives of the Lagrangian function with respect to the exogenous variable at the optimal solution of the problem. Del L by del alpha will be equivalent to dv by d alpha. Okay. Using the envelope theorem, the Lagrangian multiplier can be presented as, we did this solution dc by dq, where capital C is basically the value function. This will be similar to, dl by dq or del L by del q. Okay, so that will be similar to del of the Lagrangian expression. This L indicates the Lagrangian expression. This C is the and the L here okay, and Q is fixed because it is a cost minimization problem, so Q is equal to Q. Q is the parameter of the model. In case of cost minimization, Q is the exogenous variable or the parameter. It is fixed. Any question? So last day I used the term applying Young's rule and envelope theorem. So while I used this term envelope theorem, I told you without the idea of envelope theorem also we can proceed, because already we solved for this kind of thing. Actually, when we consider the envelope theorem, we indicate this. We can take the derivative of the Lagrangian expression with respect to parameter. Alternatively, we can take the derivative of the value function with respect to parameter. Okay. Okay, so do anyone have any kind of question from the optimization, constraint optimization, especially? Okay, so up to this will be your syllabus.